So thanks a lot for inviting me to this beautiful, beautiful city. I've been to Paris before, but only, I'll come here for 2 days, go to touristy places, leave. But this is really a great city. I'm very happy walking around. And the workshop, I've been here for a month, and the previous workshop was also very good. It was the inference workshop. But this is better. This seems to be more filled. And of course, I'm here. So we are talking about, we'll be talking about information theoretic secrecy and interactive communication. More of this, less of this one. But still, the reason we keep this in the title is because the methods that we propose, actually their advantage is that they allow for handling, you can handle interactive communication with it. And so you can derive lower bounds on some problems where you have interactive communication. It's usually tricky, but we'll propose a very simple method which will allow you to handle even interactive communication. So more of this, less of this. So I am Himanshu Tyagi. I'm at Indian Institute of Science in Bangalore. The second part of the talk will be given by Shun Watanabe, who is at Tokyo University of Agriculture and Technology in Tokyo. And this is the outline. I'll do the secret multi-party secret key agreement. Again, I'll start with two-party, and I'll point out results in multi-party secret key agreement, and then we'll derive some bounds for this problem, which will be used later by Shun in this part, where he'll look at OT and bit commitment. I think more of OT, less of bit commitment, and maybe something else, and use this bound to derive some bounds here. In the third part, third hour, which Shun will do half of, and I'll do the discussion half, the convenient half, he'll present actually an interactive protocol for secret key agreement, as opposed to the regular one-sided information reconciliation and privacy amplification approach, where you do one-side communication. Actually, there's something to be gained if you have interaction, and we'll present such a protocol in this part. So just before I start, we have been seeing some great talks till now, and this is not a tutorial by any chance. I mean, it's a tutorial in the sense that it will be simple and slow. But it's not tutorial in the sense that we won't cover the great results we are building on. We'll just present our small results. Actually, most of the great results we are building on, the authors are here. So we don't want to cover their results. But just this will be mostly single shot. We won't look at IID. We'll just give implications of our result for the IID case. One big difference from the previous talks is that the distribution is fixed, a fixed known distribution. So we can de-randomize a lot of things. So why should we be excited about a fixed distribution as opposed to minimal assumptions on the source, like just min entropy or something minimal, as we were doing till today? Well, two reasons. First reason is maybe you actually know the distribution and you can do something about it, which is actually not a bad reason. But maybe a more important reason from cryptography point of view is you can think of these as reduction arguments. Your initial distribution is what you can do computationally, like a bit commitment or an OT, which is given to a randomized OT. That's your input source. And now you want to convert it into something else. So one way to view all this is that initial distribution is something which you are given, and now we are reducing it to something else. That's another view of it. Okay, and final comment I want to make before I start. There are a lot of reductions from secure computing to secret key agreement, which are useful. That is, if you can do this problem, then you can do something here, and they are used to get bound. Today, we'll give a reduction from secret key agreement to hypothesis testing. So in effect, what we are doing is we are reducing all this to hypothesis testing. And it's quite natural, because the case we are trying to make is you can do all these things. You can generate security because the legitimate parties are in some way more are correlated than the eavesdropper. You have some advantage over the eavesdropper, and we want to capture this advantage directly in terms of a hypothesis testing problem. How far are the joint distribution from an independent distribution? If your distributions are independent, then clearly you can't do anything information theoretically. And if you are correlated, you can do something. And we want to capture this heuristic. That was actually the starting point of the work I'm about to present. Okay, so here is the model, M parties. Another difference between computer science and, let's say, information theory community is that we don't have Alice and Bob. We have parties, x1 to xm. These are correlated random variables, x1 to xm. And there's a public communication network here. Okay, so this is the public. Oh, please stop me if you have any questions. That's the whole point of this slow talk.
So you use the acronym
Where did I use the acronym?
Well, it wasn't IID. You said somebody was talking about what you were going to do. I thought you used the word
IID.
IID.
Yeah, no, yeah, sorry. I won't use a term which you won't know. Okay, okay, IID, yeah, that's right. Yeah, we'll come to it. So there are M parties and there's a public communication network. These guys are observing this correlated random variables x1 to xm. There's an eavesdropper sitting here in this communication network, which these guys can use to talk to each other. So you can send any communication here and you can do interactive communication. I'm not being very formal in defining interactive communication, mainly because I'll be focusing on converse results. So, but it's, if you want, you can think of tree protocols if you want, but it's more general. In this case, I allow more general protocols. And just for those of you who know, it's not that we label our leaves in the tree protocol with outputs. That won't do. When you come to the leaf, then you make a distributed decision. You shouldn't label the leaves with the outputs. That won't give you any gain over the eavesdropper because he'll see the entire transcript. So when you come to the leaf, you declare your output. Okay, but this is a more vague description. First party communicates, broadcast mode, everyone hears it. Then the next party communicates based on its own local observation x2 and the communication from previous party. Then so on and so forth. All communication are in the broadcast mode and you go over one as many times as you want. Again, since it's a lower bound or a converse result that I'm after, I won't be very formal here, but I'll describe my protocol by pi and the random transcript by this capital Pi. This is the random transcript, the random realization of the communication that you observe. This eavesdropper who's sitting here sees all of this communication, and let's say another correlated random variable z. Throughout, this joint distribution is fixed and known to everybody, legitimate parties as well as the eavesdropper. And after you communicate, the goal is to generate a secret key. So what do? This party has its own local observation here and also this interactive communication which was used. So looking at both of these things, it generates an estimate k1. Similarly for this second party, this has its own local observation and all the transcript pi which it has seen, so it generates k2. And just to be sure, this is a function of the local observation and pi. So just a remark, in this secret key agreement problem, we allow private coin. Each of them can flip a coin at their end, but whatever public coin is needed is included as a part of x1 to xm. If I allow separate public coin, that kills the problem. That immediately gives you the secret key. So there's no public coin beyond what is already included in x1 to xm. Okay, and this guy comes up with km. Okay, so what is a secret key? Yeah, sorry.
If you allow public coin, then it immediately kills the...
Because that constitutes, so our goal is to generate secret keys.
But it's a public coin, so it's not a secret key, then. It's a public coin.
Oh, sorry, I'm sorry. So that's a good correction. We allow public coin, but we don't allow private shared randomness. Private shared randomness. If it is there, it's already included as a part of x1 to xm. Sorry. Yeah. Okay, good. So what is a secret key? So this is the first definition. So this will be rather informal, the talk, but I'll try to do proofs formally. So what is a secret key? We have two requirements. First requirement.
Can I say more basic?
Yeah.
What is the distinction between pi and z?
Oh, this pi and z?
Yeah.
Okay, this pi is a public communication. It's a transcript of the protocol which they run. So this is the communication which was revealed to the eavesdropper. Z is something a priori side information which was available to the eavesdropper before the protocol itself. It's correlated with x1 to xm via this distribution.
Okay. So it's not what's going on the public.
It's not. So in the end, the eavesdropper will get to see z and pi.
Okay, thank you.
Okay. Right. Good. Okay. So the first requirement is what we'll call the recoverability condition. So we'll call a random variable k, a separate random variable k, which takes values in this script k. So all these random variables here are taking value in the same script k. This is a set of size, again, k, small k maybe. We'll call this random variable k a secret key if the probability that all this K1 to Km agree with K is greater than equal to 1 minus epsilon. So this epsilon is a parameter of my design. So all of them agree with K with probability 1 minus epsilon. And the secrecy condition can have many possible secret key condition. So I'll use this notation D for the total variation distance because we just have one distance in this talk. But it's just, I'll define it here maybe. So what is total variation distance between P and Q? We are looking at everything is discrete and finite for us. These random variables for simplicity are discrete and finite. So this is simply half of Px minus Qx. And just to remember, this is also sup over A, Pa minus Qa. So total variation distance is great because it gives us a measure of additive change if you change from this probability to that probability. Later on, we'll see another distance which will give us a handle over the multiplicative change if you change from P to Q, the ratio PQ. This is an additive change. Okay? So this is a good measure. It says that if you prove something to work under this P, then it works almost similarly under this Q, but this is the penalty you will pay in terms of probabilities. That's the way to interpret a total variation distance. So if you design, so what is the secrecy criteria? Secrecy criteria says if you look at the joint distribution, if you look at the joint distribution of K, your secret key, the transcript and Z, and this another distribution which is uniform over, abuse of notation, uniform over this script K, and the distribution on pi Z is independent. This distance is less than equal to delta. So this is what's happening in the real world. In the real world, you're generating this K and you're revealing this transcript pi and this Z. And this is what you want to happen in the ideal world, that the key K is like a uniform random variable which is completely independent of what was revealed to the eavesdropper. And this statement is saying that the real world is not too far from the ideal world. If you do calculations for the real world, if you do calculation for the ideal world, the calculation for the real world would be just delta off. So you can prove all your things here and then just add a delta to all the probabilities that you have.
Just to clarify, the terminals 1 to n do not know Z.
They don't have access to Z, right? They just know it through the joint distribution. Right. Okay, so we'll call such a thing an epsilon delta secret key. Such a K is called an epsilon delta secret key. Okay? And this S epsilon delta x1 to xm given Z is our notation for the minimum length of an epsilon delta secret key. Maximum length of an epsilon delta secret key, the best you can generate. So max is not right, but let's see. And the goal is to give some kind of useful bound for this guy. That's what we are after today. Okay? M parties observing correlated random variable, the eavesdropper sees Z, they talk to each other, they agree on this K. What is the maximum length of a secret key they can generate? That is, what is the maximum length of a random variable K over which all of them agree, and this random variable K is almost independent of whatever communication was used and eavesdropper's information. First question, should they communicate? Do they need to communicate? Now, this is a classical question in information theory answered a long time back by Gach and Kerner, that without communicating in general, if your distributions are not naturally decomposing into something, you can't agree on even a single bit. Even two parties can't agree on a single bit without communicating. So they must communicate in general, unless you have a very simple trivial distribution where you already have a key. So they must communicate. Now, if they communicate, they're leaking something to the eavesdropper, and you can, indirectly we are suggesting they can gain something. Maybe they can agree on more than what they communicate. And we are asking what is that more that they agree on as they communicate. And this more would be secret from the eavesdropper because he doesn't have access to this more. Okay, so we'll focus on the m equal to 2 case. So this problem, this particular problem, not this m terminal problem, but m equal to 2 version goes back to, I think there was an early version, Bennett. Yeah, please correct the spellings. Brassard, Robert. There is an 85 paper, but I think there's the 88 is the one I have read. So 85, because I saw that in previous talks you guys were citing 85. Maybe that's a conference version. Okay, this is the first early formulation. But in this clean form, I think the formulation goes back to Maurer, 90, and then a more elaborate paper in 93. And we'll talk about a particular quantity soon. And maybe I should first clarify what was that quantity. Okay, so these are the papers which introduced this problem. Now, suppose these observations in information theory for m equal to 2 case, we are mostly interested in what is called IID observation, so independent identically distributed observation. What do I mean by that? For m equal to 2, you have x1. Maybe for two parties, I'll just use x and y. Okay, x1, x2. These are my observations, and p equal to 1 to infinity, and these guys are IID. Or maybe I fix n. Okay, IID with a fixed joint distribution p x y z. This particular case has received a lot of attention, and in this particular case, what we are after is the rate of growth of this guy with respect to n. So the first order term there. So you have S epsilon delta x1 xn yn given zn, and we can define the first order term here. So we are hoping it scales with n. Let's say at least it goes linearly with n, and then we are asking for but limit of this guy, and this is what we are calling the secret key capacity. Okay, so this is the SK capacity. Secret key capacity is, let's say, the first order term in the growth of this guy. The methods we'll propose today will actually allow you to go beyond this. You can actually characterize a second order term with constant. Yeah.
So the epsilon and delta are constants.
Are constant, and they are fixed a priori. And one more thing which we'll see later is that the interesting case is when epsilon plus delta is less than 1. They are positive constant, sum to less than 1. Okay, if in the other case you can show it's infinity. This quantity can grow as much as you want. Okay, but let's say, just remember it's less than 1. Okay, so this is the fixed epsilon delta secret key capacity, but the ultimate thing is when these guys go to 0, so we can define this. Some stupid notation, but epsilon plus delta goes to 0 of this guy. Okay. So this is the epsilon delta secret key capacity, and that guy is just the secret key capacity. Okay. Epsilon delta secret key capacity, and this is the secret key capacity. If you want your leakage as well as your probability of error to asymptotically go to 0, what is the best rate that you can attain? What's the best first order term in the growth of this guy that you can attain? That's the question which initially people were after, the secret key capacity. It was studied and characterized for specific cases by Maurer 93 and Altsvida. Just 93. So we'll give an expression for this right away, and we'll see how to easily get that expression. One more remark, this was all for m equal to 2. For a general m, a problem we'll revisit later. Again, we can define the secret key capacity similarly through the same steps, and that problem was defined and studied by Chisaran Narayan. We'll come to that problem later if we have time. It was in 2004. Yeah.
If we care about we want epsilon delta to go to 0 as a function of n.
Right.
Does it change this
Yeah, and we'll give a converse which will at least get you some handle over what you can do. So maybe you want epsilon. So we'll see that only epsilon plus delta matters. That's one thing. I won't show that result actually. It's quite with this definition of secrecy, where k is not. So see, secrecy is for k, and you're agreeing on this k. I could have asked for k1 itself to be here, or k2 itself to be here. That's a more restrictive definition. There, it's not easy to combine epsilon plus delta this way. In this definition, only epsilon plus delta matters. That's a technical point. But if you want that to go to 0, let's say exponentially rapidly, e to the power minus n something, c, then what is the rate that you attain? Yeah, it will change. The answer would change for a fixed n. But if you just want asymptotic result, then the rate, the final asymptotic rate can also remain same. You can have it going to 0 exponentially rapidly also. Okay. Yeah, that's the purpose of the methods we are developing, so that we can try to answer more refined question than just this first order term. What is the relation at a fixed n between, let's say, this epsilon plus delta and the length? Okay. So this is where we are, and what is this result? This is a beautiful result which says that this first order term is a familiar mutual information. Oh, sorry. So what is the cases in which we know this result? Mutual information when z is constant. So if you say that the eavesdropper sees just the communication but nothing else, then this is a very nice, pleasing form, the mutual information between x and y. So this is defined as, for those of you who have not seen this is the right workshop for you guys, this thing. Okay, the entropy in x minus h of x given y. And a very important observation by which is simple but will help you handle the multi-terminal case due to Chesser and Henri, and this you can also think of this as h of xy minus this. Okay, so each of this formula will suggest a scheme to us. This one suggests that maybe we agree on x by communicating this much. Okay, so maybe to agree on x, I just have to communicate this much. If I'm able to do that, then the difference can be extracted as secret key, because I just sent this much. This was the randomness that we agreed on. This is the randomness that I revealed. So the difference is what we were able to gain. That's the heuristic behind this first papers. Now Chesser and Henri later noticed that, okay, this is the same expression as this one. Maybe we agree on both x and y by communicating this much. Okay, so that's also another scheme which can be built up. And the point is that this first scheme is not symmetric. For two-party, it's okay. For multi-party, the second scheme makes more sense. Otherwise, it's not clear what to agree on. So this suggests that maybe for multiple parties, we agree on everything using as little communication as possible. Okay. So we already see that this problem has two components: an error-correcting component where you have to agree on something, and then a privacy amplification component where you have to make that something you reveal to the eavesdropper independent of what you agree on. So these are the two components which this problem inherently has. Okay, so this is tight. Now another case where we know the answer is when, let's say, x, y, and z form this Markov chain. So z is like a degraded version of y or an x, or the x. And in this case, the capacity is conditional mutual information. So these are two cases in which we can give precise answers. For a general z, we have bounds, upper and lower bounds. Actually, even for this problem, we have not solved it. The bound, obviously, the bound started with these papers, and then they were improved. An improved bound was given by Maurer and Wolf in terms of what is called the intrinsic information. Then a later improvement was, I think, Renner and Wolf. Again, it's a new expression again. And the final, I think the best bound here around for this problem now is due to Gohri and Anantharam. Right, and even for the M-party counterpart of the same problem. So this problem is open, by the way. You don't know the first order answer for a general XYZ. So that's the extent to which, that's the beauty of information theory. In 5 minutes, I can state a difficult open problem. Yeah.
I lost whether you already switched back from the IID case, or are you still in the IID?
No, this is the first order term for the IID case. C. These are all the results for C, the capacity, right. So this is all for IID case, just the first order term. So what I'm saying here is that let's say for z equal to constant case, this not s epsilon delta, but roughly x and yn given x and yn, let's say z is constant, roughly it looks like n times I xy plus something which is O of n. This is very rough. That's what I'm claiming here. That this is like n times I xy plus something which is small O of n, and we also of course want to know what is happening here. Okay. 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 So now in the next, what's the time? Okay. So now I'll try to, let's say, derive some bounds for this general guy and recover these two results, but through bounds on this guy itself. So we'll derive single short bounds without the IID assumption, and this is not our work, this is well known. What is our goal with the single short bounds? They should firstly make sense in the single short setup itself. They should be good if you simulate them on the computer. That's what Professor Hayashi was suggesting yesterday, that if you give single short bounds, if you simulate them, they should be good, number one. Number two is that if you analyze them in few asymptotic regimes, let's say this is one interesting one, or what Salil was suggesting, they should at least give optimal thing in the asymptotic regime. That's what I'll call a good single short bound. And that's what we want to derive. Okay. Yeah. So a comment about this security criteria. So in the talk yesterday, I think at least we alluded to the fact that we can also analyze other things, where instead of this total variation distance, this is the KL divergence. That's another notion of security which you can have here for secret key. You can have other operational definitions, such as you can track what is the number of guesses that the adversary who sees this needs to make to guess the secret key value. And this operational definition to some extent is also equivalent to this one. We can show that. There'll be another talk. So these are these notions of information theoretic security. Stefano is giving another talk where he'll relate information theoretic notions of security to cryptographic notions of security, semantic and distinguishable security, but not for this secret key problem, but for the message transmission problem. But at least I think that talk is sort of a companion talk for this part. Okay. Okay. So, right. So schemes. So let's say generating a secret key, and this is basically upper bound, lower bound, lower bound for S epsilon delta xy given z. So there are two steps. So this is very basic for most of you, but I think I'll go through it anyway. There are two steps. First is the privacy amplification step. Or so first is the information reconciliation step. What does it mean? Information reconciliation.
When you say you mean construction, showing that you can achieve this?
Achievability result.
This is always something confusing with computer scientists. And,
Okay.
For us, lower bounds are always negative results.
Oh, so this is one thing I don't approve. so this is, yeah, I know we get reviews like that. It's very confusing. So that's why I think achievability and converse terminology is better. But this is lower bound here is achievability. This is the best I can do, and I'm saying I can do at least this much. So okay. So achievability result, what you can do. So I'll give an algo. Okay. So information reconciliation. So the first step is to agree on something. As I said, if you don't communicate, you probably don't even agree on a bit. So forget about extracting a secret key. Okay. So first we have to agree on something. These two parties have correlated random variables. Convert correlation into bit which you agree on with large probability. So very simple strategy. We wish this guy with X hopes to send its X to this guy with Y. So what is that problem? We want a set such that with large probability greater than 1 minus epsilon, if you look at this communication, you'll be able to recover X. So I'll just give a method. It's a very simple method once you see it, but it's very powerful. So single shot. So this T is like my good set, the one I would like to recover. And let's look at just this set. It's the set of those x and y such that if you look at minus log p of x given y, that is less than equal to lambda. So for the IID case, this will be you can have a very good handle over this set, because these random variables, these guys now, remember, you can think of these guys itself as a random, some random variable. And for the IID case, these guys are very close to the mean, n times the mean, and that's why you can just work with typical set, but this is all you need to complete this. Okay, well, this is the set, and what do I do? Is it a good point to introduce some more terminology? Okay. So what do? I take this x and map it randomly. So let's, f is a random mapping. This is very loose notation, which takes x and maps it to 2 to the power lambda plus gamma bits. Okay. So I know about this set. I map it 2 to the power lambda plus gamma bits. And the hope is that I can distinguish any two sequences in this set. That's what I'm hoping for. Okay. So now, what is the, sorry, lambda plus gamma. Gamma is some fudge parameter which I don't care about, something more, and lambda is coming from here. So I have some handle over this set in terms of lambda, and I'll map it here. Okay, why is this lambda plus gamma? Maybe we already note a property of this set. If you look at the cardinality of this set, the number of x for any given y such that x comma y are in this T lambda, every element in this set has conditional probability more than 2 to the power minus lambda. So there cannot be too many such elements because total probability is 1. So the maximum number of elements in this set is at most 2 to the power lambda for any fixed y, for all y. Okay, so at the receiver you know y, and once you know y, you are trying to recover x such that x, y are in this set, but there are no more than these many of these x's. So if you hash x into these many values with large probability, you will be able to recover the x. That's the idea. I won't go into details of the proof because this is not my main focus. I want to focus on the converse. But once again, this is the set which we want to recover. This decoding is I look at y and I get a hash from u. I would look for an x such that x comma y are in this set and the hash values are consistent. The property of this set is that if you fix any y, the number of x such that x comma y are in this set is no more than 2 to the power lambda. That's the property of this. Yeah. I can do it for randomly chosen function and then de-randomize to claim there will be a fixed function which does that. Not at all, because I fixed the distribution. It should be important for you. So in this case, I can de-randomize whenever I want because the distribution is fixed throughout, a single distribution. So I can do this proof with randomized function, and then since the randomized function work, I'll say there must be at least one which works.
What if you just live with the randomized function?
No, we can do that also. We can allow randomized functions. Our protocols do allow. No, so I'm a bit. Yeah, sorry for this secret key problem. Maybe it's better to de-randomize for this function part. Maybe.
You can send the function across. It's not a problem.
Yeah, that's right. Okay, good. So if you use not just a random function but a more structured thing coming from a 2 universal hash family, which we'll see soon, then you can maybe send the function also across.
If you don't have any bounds on running time anyway, why not send the whole function?
No, I have to keep a track of this, the rate of communication which I'm sending when I do the second step, the privacy amplification part. So I don't want to reveal too much over this public channel. Maybe it goes through, but it goes through.
You're revealing something uncorrelated.
Okay. Okay. Yeah, maybe it goes through. Okay. So what is the length of this function now? Something like lambda plus gamma in abstract. That's the number of bits I want to communicate. So let's see what are we saying for the IID case. So for IID case, do we have a handle over this gamma, this lambda? So for IID case, this random variable here looks like minus log p n x given y. This is summation I equal to 1 to n log of p xi given yi, and by your favorite concentration result, and maybe you can say something more here also, but at least we know this. Okay, it will be close to this guy, and that's why in the that's why you are kind of sending this much communication in the IID case. Okay, this is building towards a result of h of let's say h of x minus h of x given y. So we are able to get h of x given y with this single shot result. What is this quantity in the single shot case? This quantity has a name which we have already encountered, so it's good to point it out. Suppose this was the entire support. Suppose there was nothing outside it. Then this is the maximum value of this guy. And this is essentially what we were calling the max entropy of x given y. But this is not the entire support. This is only a set of, we want lambda such that, what do we want out of lambda? We want lambda such that this guy has large probability, right? That's the lambda we want. So this is just a large probability set. It's not the entire support. Okay, so this thing is what we'll call the epsilon smooth max conditional entropy. So this is h max xy. We'll define this guy first. This is defined as max over xy minus log p of, okay. That's one definition. There can be other definitions which you can think of. And epsilon smooth is this smoothing idea which we have been encountering in the last few tutorials also, talks also, that you don't want to compute it for this particular distribution, but for some other distribution which is not too far from this distribution. In fact, you can simplify this calculation a little bit if you allow something more than distribution, just subnormalized functions. So like distribution, non-negative functions which add to something less than equal to 1, not necessarily equal to 1, because we want to allow this as my set. So you can define it as min h max of, so this is a notation again similar to this one, where what are we saying about qxy, where qxy is a subnormalized non-negative function which is not too far from pxy. So pxy qxy is less than equal to, let's say, epsilon. So what is our definition, good definition for qxy here? Well, here is a good definition. It's just pxy times the indicator function t lambda. So it will be 0 if you're outside t lambda, but it will be 1 if you're inside t lambda. And since this set t lambda has probability greater than 1 minus epsilon, you can verify that the distance between these two defined, but this is not, forget about this part for now, defined this way because it's not a probability. So defined that way will be less than equal to epsilon. So this is the max conditional entropy, and this is the epsilon smooth max conditional entropy. So what are we saying? We are saying that we can send x to y using as many bits as the epsilon smooth max conditional entropy. That's what we are saying here. Okay. Okay. Pause. Any questions? You can correct it, please.
Max entropy is usually defined by using the support size.
No. So yeah. No, so I'm defining it as the max because I want to keep track of this. No, it's not h infinity.
No, it's not h.
H min is, it's not h zero, you mean?
Yeah, it's not h0. H0 is the support size.
Which is also the support size bound here. But I think this also is fine for this problem. So he's saying that maybe we can define h0 in terms of support size, which again will satisfy the same bound here, and it will go through. But I think operationally this makes more sense to me because max of entropy and the min is the min of this, what was called sample entropy in the first talk, I think. Okay. Okay.
usually max entropy defined as the number of cycles.
Right. Size of support. First, you will define support of px given y, right?
Maybe, but there is a way for the definition of max entropy condition because you can optimize the Q or something. So there is a two way. So I cannot say differently.
Okay.
So
but this works, right? This one works here.
Maybe.
Okay. So actually, this is a good point in the sense that this definition of conditional entropies and max and min conditional entropies can only be fixed once you give a lot of operational significances for those definitions, like the conditional entropy. Here, as you probably already noticed, there are many definitions around because we kind of also construct them based on our convenience, and they look like the right quantities. And there are some basic things we want from them. In the limit, they should go to the right quantities, for instance. Okay. Okay, good. So that's Shun is watching, looking at his watch. Okay. So we have agreed on X using this much communication. Now, the second step is to now get a secret key out of it. Yeah.
So in this example, you fix the communication length, right?
Up to this point, I've just agreed on X using communication of.
But importantly, you fix the hash length.
I fixed the hash length, yes.
But you can also adapt, in the non-IID case, it makes sense to adapt the hash length to the probability of X, right? And
that's what Shun will do at the end. So this is, yeah, that will require interaction. So when we come here, that's what we would like to do.
You can do it non-interactively, right?
We'll see. We'll see. Because it's P of X given Y, no single party doesn't know X given Y. Okay. Okay, so second step is generating a secret key out of it. So we have now agreed on X. And how do we extract a secret key out of it? And this is a step in, how much time do we have? 5 minutes. Okay. So I think this plan would change a little bit. This is quite a bit maybe. So this is a step which we all know about. Maybe I'll just rush through this step. We have seen this leftover hash lemma coming up several times now. And so I don't want to state it. Maybe, Shun, do you need the leftover hash lemma in your part? You need the statement?
Yes.
Okay.
But I guess maybe just.
Okay, yeah, okay. Okay, okay. So maybe I'll just give the statement. So suppose F is a 2 universal hash family. What is a 2 universal hash family? If you look at these functions F coming from this family, F is a family of functions from X to, let's say, K bits. This is a 2 universal hash family. If you take any X and X prime which are not equal and estimate this probability that you take 2x and x prime which are not equal and map them to the same value, this should be a very small probability. So this is like almost invertible. This average probability here is less than equal to to the power k, the range size. Okay, and random functions, for instance, would satisfy this. That's the property we want. Suppose you have such a 2 universal hash family, and now if F is chosen uniformly over this family, then we want to get some bound on the total variation distance between P of Fx, Z, and a uniform distribution over the range of F, so k bits times Pz, and I'm writing expected value over F, but this basically means you can also reveal, suppose you can put F here also, so you can also reveal F to the eavesdropper. So this quantity here, this is the leftover hash lemma, is less than equal to half 2 to the power k, actually, yeah. So first, a very simple form is this, h min of x given z.
F is independent of x and z.
F is, yeah, independent of x and z. F is just uniform independent of x. So this is less than equal to this. So it's saying that you can extract roughly as many bits as h of x given h, min entropy of x given z. Yeah.
What is the probability taken?
This one, oh, sorry. Yeah, this is fine. Thanks. Okay, this is the primary form. And now another form which we want to use in our bound is that if you don't have one z but you have two random variables, let's say z and z prime, but z prime is a finite size random variable. So in this case you can use another bound just based on evaluation of this one kind of thing. 2 to the power k minus h min of x given z plus log of cardinality of the other guy. So if you here's a way to read it. If your eavesdropper is getting a z, another random variable z prime, which has cardinality L, then the number of bits independent of z and z prime that you can extract from x is h min of x given z minus L. Okay, h min of x given z minus L is what you can extract. Now, in our example, this z is the regular z. The z prime is the communication that we revealed from that scheme. It has a length h max. And so by this leftover hash lemma, we can extract we can extract these many bits, h min of x given z minus h max, and I had an epsilon here of x given y. Okay, this is just by this statement, because I can extract h min minus this guy. This guy in our case is just h max there. That's the scheme we used. We just revealed these many bits. This quantity is still not very useful, because if you apply it to IID case, what is the h min? It's the minus n times minus log of the minimum probability of x given z, and sorry, maximum probability of x given z, and that's not good. So we again use a smoothing idea. I'm rushing through this part. So note that if instead of this given distribution on xz, I had some other distribution by triangle inequality, I would be off by just the distance between those two distributions. So I can do this evaluation for some other distribution which is close to, let's say, close to xz, and I'll just lose a delta which I'm allowed to use. So I can do sort of delta smoothing here, and the max over that delta is defined as that max over that q, which is delta close to pxz, is defined as the delta smooth min entropy. So this is roughly the answer that I get. Okay, and so for the IID case, this is approximately equal to this, and this one here is approximately equal to this times this. So what have we attained? We have shown that S for IID, this guy here, is at least n times h of x given z minus x given y, plus something which is very small, maybe O of n, and this basically gives you the first part. C epsilon plus delta is greater than, actually just the C epsilon, C x y given z is greater than h of x given z minus h of x given y. Okay. So you can see if z is constant, it gets you the thing I was claiming, and even if z is a Markov chain, if x by z form a Markov chain, then it also gets you the bound I was claiming. But this is a general achievability using just one side communication from x to y. There was no feedback. So is this tight? How can we show these bounds? The other side. So in the next talk, after 3-hour talk by Professor Chisser, we'll see one method of doing it, namely based on Fano's inequality and some properties of interactive communication, chain rules for entropy. A very nice, elegant proof. There's another method based on monotones, which I think is, so it's come out in 2 works. So one is by Renner and Wolf, and second is by Gori and Anantharam. I think you call it potential function method. So by just noticing some properties of this function itself, and the fact that this function proceeds in some monotone fashion as you increase the as you go along the protocol, you can get some bounds. That's another popular technique. Leo, can I go 5 minutes over, or should I then I eat into Shun's stuff? Huh? Okay. Okay. They're pretending to pay attention at least. Okay. And the third method which we want to do today, which gives us something which the previous methods were not giving, namely the fact, for instance, that this guy C epsilon delta will not depend on epsilon and delta, is what we call the conditional independence testing bound. Okay. So what are we saying? Why can we generate secret key? Well, we can generate secret key because your distribution is this and not this. If it was this, that is given z, x and y are conditionally independent, then there is no hope of generating any secret key. You have no advantage over the eavesdropper. Okay? So the point we want to make is you can generate a secret key because you are here, not here. And so somehow the length of your secret key should give you a measure of distance between these two, some measure of distance between these two. So we want to give a reduction argument. We're using a secret key. We would like to distinguish between these two probability distributions. So given the secret key agreement protocol, we'll construct a hypothesis test for this one versus this one. Okay. So I think maybe I'll continue in the next part, just first 10 minutes. Okay. I think I'll take the next 10 minutes. This is a good time for break, because after that I'll have a proof. Okay, so that's what I want to do. I want to give this reduction to a hypothesis testing problem when we come back.